Welcome back, everyone. In this part of the course, we're going to be talking about the order process, specifically how the order flow works in our e-commerce application, how the cart connects to checkout, and why we're designing things store by store rather than all at once. This is a really important section because it ties together everything we've built so far. So let's dive right in. So let's quickly orient ourselves. Up until this point in the project, we've already completed two major milestones. User login and authentication is done, and the add to cart functionality is fully working. Those are checked off. What remains is the order-related work. Specifically, we need to handle order placement, then we need the store to be able to see those orders, and finally, users should be able to rate products after purchasing. These are the three remaining pieces, and they're actually not that complicated. So the three remaining features are first, order placement. The user goes through checkout and an order is created. Second, the store needs to be able to see that order on their end, so the shop owner has a dashboard or view where incoming orders appear. And third, after a user has purchased a product, they should be able to leave a rating for it. These are described as small, manageable features, and the expectation is that all of this can be wrapped up comfortably by Sunday, so the timeline is very realistic. It's also worth noting where we are in the overall course. There are only about 2 classes left. Once the course wraps up, that's when discussions about internships and any additional requirements will happen. So if you have questions about what comes next professionally, hold on to those for then. And of course, if anything in the material is unclear, don't hesitate to ask. The door is open for questions throughout. Now, let's talk about the cart page and a specific design decision that was made. Originally, there was a Checkout All button. The idea being that a user could check out everything in their cart at once, regardless of which store the items came from. But this button has been removed from the design. Why? Because it introduces a lot of complexity. Here's the core problem with Checkout All. Imagine a user has items from 2 different stores in their cart. If they hit Checkout All, you now have to send order data to store A and store B at the same time, as separate entities. Each store needs its own order record. The data flow becomes complicated, and it's easy to get confused about which items belong to which store. It's technically possible, but it makes the system significantly more complex. So the decision was made to remove it entirely and go with a store-wise checkout approach instead. So here's how store-wise checkout works. When a user goes to checkout, instead of one big combined order, the system creates a separate order for each store. So if you have items from Sudham Shrestha's store and items from another store, you get 2 separate orders. Order 1 for Sudham Shrestha's store and order 2 for the other store. Each store only sees its own order. This keeps the data clean, the flow simple, and each store's order management completely independent. This is actually how real-world platforms like Dara's work too. You might think that when you order from Dara's, it's all one big order, but actually, products from different sellers arrive separately because each seller has their own order. It might look like one checkout experience on the surface, but underneath, the system is creating store-wise orders. So what we're building follows the same industry standard pattern. Our approach is consistent with how professional e-commerce platforms handle multi-store carts. From an implementation standpoint, removing the Checkout All feature is actually very straightforward. You don't need any AI tools or complex refactoring for something like this. Simply use Ctrl+F to search for Checkout All in your code file. Find the relevant line or button element and delete it. It's a simple cleanup task. The point here is that not every change in a project requires sophisticated tooling. Sometimes you just find the code and remove it. So now we know what the cart page looks like conceptually. It shows items grouped by store, and the Checkout All button has been removed. The next question is, what actually happens when a user clicks the Checkout button for a specific store? Right now, we're on the cart page, and clicking Checkout should take us somewhere. It should trigger some action. Defining exactly what that action is and where it leads is the next thing we're going to work through. Continuing from where we left off, let's talk about the checkout mechanism. Now, the original idea was to have a dedicated checkout page where users would review their order details before paying. But here's the key insight. All the data we need is already available. The user ID comes from the logged in session, the shop ID is already in the URL, the status is auto-generated, and the total amount can be calculated from the cart. So the decision is made to skip the checkout page entirely and redirect the user straight to Culti, the payment gateway, when they click the checkout button. When the checkout button is clicked, the app tries to call a checkout function inside the cart controller, but that function simply doesn't exist. The route is defined, it reaches the controller, but there's no matching method. This is clearly shown in the error. So the fix isn't just adding a function. The instructor decides to create a brand new order controller dedicated to handling the checkout and order logic. This keeps the code organized and follows the single responsibility principle. Here's a fundamental web development concept that comes up here. The checkout button is currently inside an anchor tag, an A tag, which means it uses the get method. But get is for retrieving data, not saving it. Whenever we need to save data to a database, we must use the post method. So the instructor converts the anchor tag into a proper HTML form with method post. This also allows us to include a CSRF token, which is a security measure Laravel requires for all post requests to prevent cross-site request forgery attacks. Here's what the conversion looks like in practice. The old anchor tag is removed and replaced with a form element. The form uses post method, and the action points to the checkout route with the shop ID. Inside the form, 3 important things are added. First, the CSRF token, using Laravel's @CSRF directive. This is a security requirement. Second, a hidden input field that carries the total amount. Hidden means the user can't see it on the page, but it gets submitted with the form. And third, the submit button, which visually looks exactly the same as the old checkout button, preserving the UI design. The instructor emphasizes that small things like this should be typed manually, rather than relying on AI tools. Now, the total amount needs to reach the backend somehow. There are 2 approaches. The first is to recalculate the total on the backend inside the new checkout function, but that means duplicating the calculation logic that already exists in the cart controller. The second approach, which the instructor chooses for simplicity, is to take the total that's already calculated and displayed on the cart page, put it into a hidden input field, and send it along with the form submission. The instructor does acknowledge that sending values from the front end is not the most secure approach. A determined user could manipulate it, but for the purposes of this implementation, it gets the job done cleanly. The instructor creates a new file called order controller inside the front-end controllers folder. This controller will handle everything related to orders, starting with the checkout function. The checkout method accepts 2 parameters, the request object, which carries all the form data, and the shop ID from the URL. The route is also updated. It's changed from a get route pointing to cart controller to a post route pointing to the new order controller. As a first step, the function simply returns the request data, so we can verify what's coming through before writing the actual save logic. After submitting the form and temporarily returning the request data, the instructor can see exactly what's coming through. The CSRF token is there, the total amount is there, labeled as total_amped, and the shop ID is also present. Now let's map this to what the order model needs. The user ID comes from the authenticated session using auth user ID. The shop ID comes from the URL parameter. The total amount comes from the request. And the status fields, order status and payment status, are automatically set to pending by default. All the required data is confirmed to be available. Now the instructor writes the actual save logic. Using Laravel's Eloquent ORM, a new order record is created with 3 fields: the shop ID taken directly from the URL parameter, the total amount from the request, and the user ID from the authenticated session using auth ID. The status and payment status fields don't need to be set explicitly because the database migration already defines them with a default value of pending. This creates one clean row in the orders table, representing the overall order. But this is only half the story. The order record alone doesn't tell us which products were ordered. After saving the order, there's still a critical piece missing. The orders table only stores the summary, shop, user, total. But what about the individual products? If a user had 2 items in their cart, we need to record each of those items separately in the order items table. This is a classic one-to-many relationship. One order can have many order items. Each order item stores the product ID, quantity, and amount for a single product. Without this, we'd know an order was placed but have no idea what was actually ordered. Here's an important detail. A user's cart might contain items from multiple different shops. When they check out from one specific shop, we only want to save the order items that belong to that shop, not everything in the cart. So the cart items are fetched with 2 filters. The user ID must match the logged-in user, and the shop ID must match the shop being checked out. This is how the instructor references the cart controller logic and adapts it here. The result is a filtered collection of only the relevant cart items for this particular checkout. To save multiple order items, the instructor uses a for each loop. For each item in the filtered cart items collection, a new order item record is created. 4 fields are populated: the order ID, which is the ID of the order we just saved a moment ago, so the relationship is established, the product ID from the cart item, the quantity from the cart item, and the amount from the cart item. This loop runs once for each cart item. So if there are 2 items, 2 order item rows get inserted. If there are 5 items, 5 rows get inserted. The number of iterations matches the number of products being checked out. Here's the complete checkout function all in one place. Step 1, save the order with shop ID, total amount, and user ID. Step 2, fetch the cart items filtered by user and shop. Step 3, loop through each cart item and create a corresponding order item record, linking it to the newly created order via the order ID. Step 4, and this is interesting, the cart deletion is commented out for now. The instructor explains that once an order is placed, those cart items should be removed, but for testing purposes, it's left in place so the test data doesn't disappear. Step 5, redirect the user to the home page. Later, this redirect will be changed to go to Culti instead. After running the test, the results confirm everything is working correctly. The success toast message appears saying order placed successfully. In the database, the orders table shows exactly 1 new record with the correct shop ID, user ID, total amount, and both status fields set to pending. The order items table shows 2 records, one for each product that was in the cart, both linked to the same order ID. The product IDs, quantities, and amounts all match what was in the cart. The order saving mechanism is fully functional. Now that the order saving is working, the next step is to replace the temporary homepage redirect with an actual redirect to Culti. The full flow will work like this. The user clicks checkout, the order and order items are saved to the database, then the user is redirected to Culti's payment page with the total amount. On Culti's side, the user either completes the payment or cancels. After that, Culti redirects the user back to our website. This return redirect is what we call a callback. In the callback function, we'll update the order's payment status based on whether the payment succeeded or failed. Integrating Culti is the next major piece of this implementation. Continuing from where we left off, let's now look at how to actually integrate Culti as a payment gateway into a project. The first thing to do is check Culti's official documentation. You can find it by searching for CultiDoc or going directly to doc.culti.com. Once you're there, navigate to the ePayment Gateway and Web Checkout section. This is where Culti provides everything you need, including a sandbox merchant account specifically for testing purposes. One of the most important concepts to understand here is the difference between the sandbox environment and the production environment. The sandbox is purely for testing. It simulates real payment flows without involving actual money. Now here's the key insight. The code you write for sandbox is exactly the same as the code for production. The methods, the API calls, the logic, all identical. The only 2 things that change are the token and the URL link. So when you're ready to go live, you simply swap out the test token for the real token and update the URL. That's it, no rewriting code. To get started with testing, you need to create a sandbox merchant account. The Culti documentation provides a sign-up link for this. You fill in your details and click Join. Now, here's something that trips people up. When it asks for an OTP, do not wait for an email. In the sandbox environment, the OTP does not arrive via email. Instead, you need to manually enter the OTP that Culti provides in their documentation. Just use that pre-given value. For production accounts, there's a separate sign-up link, but for now, we're focused on testing. Culti provides a set of test credentials for use in the sandbox. This includes test phone numbers, a test PIN, and a test OTP. Now, a practical note here. Not all of the provided phone numbers will work all the time. The sandbox environment can occasionally be down or have issues with specific numbers. If one number doesn't work, just try another one from the list. Also, if something breaks on Culti's user interface side during testing, that's Culti's problem, not yours. Their sandbox can have its own downtime. Don't panic, just try again or use a different test number. Once you're inside your sandbox merchant account, go straight to settings. You don't need to explore the entire dashboard. The only thing you need from here is the secret key. Culti provides both a public key and a secret key, but for this integration, only the secret key is required. The public key is not needed. Copy that secret key and store it in your project's .env file. That's the .env file, where environment variables are kept. The variable name should be written in all capital letters, like Culti secret key. This keeps your credentials secure and out of your source code. Let's be very concrete about this step. After copying the secret key from the Culti merchant settings page, open your project's .env file and add a new line. Write Culti secret key in all capital letters, followed by an equal sign, and then paste your secret key value. That's the standard convention for environment variable names, all caps. This is the only Calty-specific value you need to store. The public key is not required here, so don't worry about it. And as always, with any secret key, make sure your .env file is listed in your .gitignore, so it never gets pushed to a public repository. Now that the secret key is stored in the environment file, the next step is writing the actual integration code. Think back to when APIs were built earlier in this course. When making API calls, the server required a token for authorization. The same concept applies here. Calty's API also uses token-based authorization, and that secret key you just stored is what gets sent as the authorization token when your backend communicates with Calty servers. This is the bridge between your application and the payment gateway, and it's what we'll be building out next. Continuing from where we left off, let's talk about how authentication actually works when calling an external API like Calty. The concept here is the same one we used when we built our own API earlier. We sent a bearer token. That token is essentially the credential that proves who we are to the API. In Postman, we practiced passing this token manually. Now, in an actual project, we need to do the same thing programmatically. Now, how does the authorization header actually look? The documentation shows a format where you write the word key, then a space, then your actual secret key. But here's an important thing to understand. The colon and curly braces you see in the documentation are not literal characters you type. They are just placeholders used in the documentation to indicate where your value goes. The actual syntax will change depending on the programming language you are using. So don't get confused by the formatting. Focus on the concept. The authorization header needs the word key, a space, and then your secret key value. Before we start making API calls, let's organize our URLs properly. The Calty base URL, which is the testing endpoint, should be stored in the .env file. This way, if we ever need to change it, we don't have to hunt through our code. We just update the environment variable. One important detail, remove the trailing slash from the base URL. If you keep it and your endpoint also starts with a slash, you'll end up with a double slash in your URL, which will cause problems. To start a payment with Calty, we need to hit their payment initiation endpoint. The method is post and authorization is required. This structure should look familiar. It's exactly like the API documentation we built ourselves. There's an endpoint, a method, an authorization requirement, and a payload. The payload is the JSON data we send along with the request, just like when we sent JSON data in our own API. Let's go through each field that Calty requires. Let's go through each payload field. The return URL is where Calty will redirect the user after they complete payment. This is our callback route. The website URL is simply our application's base URL. The amount is critical. Calty requires it in paisa, not rupees. Since 1 rupee equals 100 paisa, you must multiply your order total by 100 before sending it. The purchase order ID is the ID of the order from our database. And the purchase order name is a label. Since we might have multiple products in one order, we can just use something like order has followed by the order ID. The remaining fields are optional, so we don't need to send them. We need 2 routes for the payment flow. First, an order history route. This is where users can see their past orders. Second, and more importantly, a callback route. This is the URL we give to Calty as the return URL. From Calty's perspective, it's just a redirect. They send the user back to this URL after payment. But from our perspective, it's a callback. It's where we handle what happens after the payment is completed. So we name it order.callback. When Calty finishes processing, the user lands on this route, and we can verify the payment there. Now let's look at the actual code. Laravel provides an HTTP facade that makes it easy to call external APIs. We use http.withHeaders to attach the authorization header. Inside the headers array, we set the authorization key to the string key, that's the literal word key, followed by a space and then our Calty secret key pulled from the environment file. Then we chain the post method, passing in the full URL, which is the base URL concatenated with the endpoint path, and the payload array. The amount is multiplied by 100 to convert from rupees to paisa. Notice how we split the URL into 2 parts, the base URL from the environment and the endpoint path. You can also write the full URL directly if you prefer. Both approaches work. Let's zoom in on the authorization header, because this is where many people get confused. The header name is authorization, that's the key. The value starts with the literal word key, capital K, followed by a space, and then your actual secret key from the environment file. This matches exactly what the Calty documentation describes. And remember, authorization information is always passed in the request headers, not in the request body. That's a standard convention across virtually all APIs. When testing, you might encounter this error. Authentication credentials were not provided. This means the request was sent without the authorization header. The API requires authentication, but we forgot to include it. The fix is straightforward. Add the with headers method before the post call and include the authorization key with the correct format, the word key, a space, and your secret key. Once that's in place, the API will recognize your credentials and process the request. After fixing the authorization header and making the request successfully, we get back a response from Calty. The most important field in this response is the payment URL. This is the link we redirect our user to so they can complete their payment on Calty's platform. The response also includes a PIDX, a payment index identifier, along with expiry information and the order details we sent. This payment URL is what we need to capture and use to redirect the user.
Here's an interesting challenge with the Calty API response. Ideally, when we get a response back, we'd like to check a success field. If it's true, proceed. If it's false, handle the error. That's a clean pattern. But Calty's response doesn't include a success field at all, so we can't simply write if response success equals true. Instead, we need to think of another way to determine whether the request succeeded. For example, checking whether the payment URL is present in the response, or checking the HTTP status code of the response. This is a real-world quirk you'll encounter with third-party APIs. They don't always follow the patterns we'd prefer.
Picking up right where we left off, after the user completes payment on Calty, Calty redirects them back to our application's callback URL. This callback URL receives a bunch of data in the query parameters. Out of everything that comes back, the two most important pieces of information we need are the purchase order ID and the status. The purchase order ID lets us find the correct order in our database, and the status tells us whether the payment was completed, canceled, or something else. Inside the callback function, notice that this is a GET method, not a form submission. The data is coming in through the URL query parameters. Now, there's an important syntax difference here. When data comes from an API redirect like this, we use array bracket notation, $request, then the key in square brackets, rather than the arrow notation we'd normally use for form inputs. This is a subtle but critical distinction. Using the wrong syntax will cause errors. We find the order using the purchase order ID, then update the payment status with whatever status came back from Calty. Before the callback, we need to actually send the user to Calty. After we get the response from Calty's initiation API, the response contains a payment URL. We redirect the user to that payment URL. One thing to be very careful about here, the trailing slash at the end of the URL matters. When we're sending payload data along with the request, that trailing slash must be present. Leaving it out can cause the request to fail in unexpected ways. It's a small detail, but it can cost you a lot of debugging time. For testing the Calty integration, Calty provides test credentials. The PIN is 4 ones, 1111, and the OTP is 987654. It's worth noting that among the test phone numbers provided, the last one in the list tends to work reliably. The earlier ones may not. Once you enter these credentials and confirm the payment, Calty marks it as successful and redirects back to our callback URL. This is how we verify the full end-to-end flow is working correctly. During testing, a data truncation error appeared. This kind of error happens when the value you're trying to save doesn't match the column's defined type. In this case, the payment status column in the database is defined as an enum, meaning it only accepts specific predefined values, like pending, completed, or canceled. If the value coming from Calty doesn't exactly match one of those options, the database rejects it and throws this truncation error. The fix was making sure the correct column name, payment status, was being used, and that the value being stored matched the enum definition. It's important to understand the distinction between two separate fields here. The order status field, which tracks whether the order has been fulfilled, stays as pending even after payment. That's because fulfillment is the shop owner's responsibility. They need to physically prepare and ship the order. The payment status field, on the other hand, is what gets updated from the Calty callback. Once Calty confirms payment, payment status becomes completed. These are two completely separate concerns, and mixing them up is a common source of bugs. After saving the order with the updated payment status, we redirect the user to their order history page. This gives the user immediate feedback. They can see their order listed with the updated payment status. The order history query fetches all orders belonging to the currently logged-in user by matching the user ID against the authenticated user's ID. This is a clean, user-friendly flow. Pay, get confirmed, and land on a page that shows your order history. For the order history page design, the approach taken here is to reuse an existing cards page layout and adapt it for order history. This is a practical time-saving technique. Rather than building from scratch, copy the cards page structure and modify it to display order data. Each card represents one order, showing details like the order ID, product name, amount, payment status, and order status. This gives users a clean, readable view of all their past orders. Let's walk through the complete normal checkout flow. The user has items sitting in their cart. When they click Checkout, the system loops through each cart item one by one. For each item, it saves a corresponding record into the Order Items table, and then immediately deletes that item from the cart. So the cart items are moved, not just copied, into the order items. Once all items are transferred, the order record is created with a pending payment status, and the user is sent off to Culti to complete the payment. Here's a really useful debugging insight. When the order history page was first loaded, there was a group by null error appearing in the query log. This is a telltale sign that a relationship is returning null, meaning the relationship name doesn't match what's defined in the model. The issue was that the relationship was being called using camel case, order items, but the actual relationship method in the model was defined using snake case, order underscore items. In Laravel, relationship names should consistently use snake case. This kind of mismatch is easy to miss, but causes the relationship to silently return null, which then breaks your queries. Reading query logs carefully is one of the most effective debugging techniques available. When you see group by null in a query log, that's your signal that something in the relationship chain returned null. Instead of guessing, you can trace it directly. Look at what relationship name you're calling in the view or controller, then check the model to confirm the method name matches exactly. In this case, the fix was straightforward. Change the relationship call from camel case to snake case to match the model definition. This approach lets you pinpoint errors quickly and precisely. A robust payment integration must also handle the case where payment was not completed. If the user abandons the payment or if something goes wrong on Culti's side, the callback still fires, but with a status that isn't completed. In that scenario, we should not update the order's payment status to completed. The conditional logic should check whether the status coming back is actually completed before making any changes. If it's not, the order stays in its pending state. This prevents false confirmations and keeps your data accurate. To make the order history page easily accessible, a navigation link should be added to the site header. This way, users don't have to complete a purchase to view their past orders. They can navigate directly from anywhere on the site. The link uses the named route order.history, which keeps the code clean and maintainable. If the route URL ever changes, you only need to update it in one place, the route definition, rather than hunting down every hard-coded URL across your templates. Picking up right where we left off, let's talk about the payment retry logic. So the question is, what happens when a user places an order but the payment doesn't go through? The instructor had initially written this feature into the codebase, and while he temporarily removed it to simplify the flow, he walks through how it works so students understand the concept. The core idea is simple. If a payment fails or stays pending, we need a mechanism to let the user try paying again without creating a brand new order. Now, the instructor clarifies why he removed the retry payment code for now. In the current demo, the payment goes through directly. There's no cancellation happening, so the retry scenario doesn't come up naturally. But he's very clear that keeping this feature in a real application is absolutely the right call. In real-world scenarios, payments fail all the time. Network issues, user abandonment, gateway timeouts. When that happens, the order ID and the total amount are already in the database. We don't want to create a new order. We just want to retry the payment for the existing one. That's the whole point of retry payment logic. So how do we actually implement this? The instructor shows that you don't even need a form for this. A simple anchor tag, an HTML A tag, is enough. You define a named route, something like payment.retry, and pass the order ID in the URL. The route is defined as a get route, order/the order ID/retry. The named route is payment.retry. Then in the view, you just create an anchor tag that points to this route with the order's ID. When the user clicks that link, they're taken to the retry payment controller method, carrying the order ID with them. Clean and simple. Here's what the retry payment controller method looks like. The method receives the order ID from the URL. First, it finds the existing order from the database using that ID. Then, and this is the key insight, it makes the exact same API call to Culti that was made during the original checkout. The URL is the same Culti endpoint, the authorization header with the secret key is the same, the return URL, the Culti callback, is the same. The amount comes from the order's total amount stored in the database. The purchase order ID is the same order ID. Everything is identical to the original payment initiation. The only difference is that instead of getting the order data from a fresh checkout form, we're pulling it from the database. Let's compare the initial payment and the retry payment side by side. The Culti API URL, same. The authorization header? Same. The return URL for the callback? Same. The website URL? Same. The amount? In the initial payment, it comes from the checkout form. In the retry, it comes from the order already saved in the database. The purchase order ID? In the initial payment, it's a newly created order. In the retry, it's the existing pending order. And critically, no new order is created during a retry. We reuse what's already there. This is why the implementation is so clean. Almost everything is copy-pasted from the original payment logic, with just the data source being different. The instructor demonstrates this live. There's an order number 6, sitting in the database with a status of pending. The user clicks the retry payment link. The retry payment method is called. It fetches order 6 from the database, grabs the total amount, and hits the Culti API. The user then completes the payment on the Culti interface. Once done, the Culti callback fires, and the order status in the database is updated from pending to completed. The instructor verifies this directly in the database. Order 6 is now marked as completed. The retry flow works end-to-end, and it reuses the exact same callback and status update logic as the original payment. The instructor also makes a quick but important UX improvement, sorting orders so that the most recently placed order appears at the top of the list. By default, database queries return records in the order they were inserted, meaning the oldest order shows up first. That's not great for users who want to see their latest order right away. The fix is simple. Add an order by on the created at column in descending order. Now, order 6, the most recent one, appears at the top of the list. This is a small change, but it makes a big difference in usability, both for the customer viewing their order history and for the shop owner reviewing incoming orders. During the live session, the instructor runs into a fail-to-load error, a syntax error that was causing the order detail view to break. After investigating, the problem turned out to be a simple naming mismatch. The code was trying to access the relationship using order items, but the actual relationship method defined in the order model was called items. So the fix was straightforward. Change order items to just items in the view. This is a very common mistake. When you define a relationship in a Laravel model, the name you use to access it must exactly match the method name. A small typo or naming inconsistency like this can cause the entire page to fail to load. The instructor then outlines what's left to build. One important feature still remaining is the review system. The rule is a user can only give a review after the order has been marked as delivered. This is a common and sensible constraint. You don't want users reviewing products they haven't received yet. The flow works like this. The user places an order, the shop views the order, the shop changes the order status to delivered, and only then does the option to leave a review become available to the user. The instructor notes that 2 steps remain to complete the full application, and these will be covered in the next session. A student asks whether other payment services work the same way, and the answer is yes, almost universally. Whether you're integrating Culti, eSewa, Stripe, Razorpay, or any other payment gateway, the fundamental flow is identical. You hit their API with the required tokens and order data, they redirect the user to their payment page, the user completes the payment, the gateway fires a callback to your application receives the callback and updates the order status. The differences between gateways are in the details, what tokens they require, what the endpoint URLs are, what fields are mandatory. That's why reading the documentation is essential. And the instructor reassures students that in a real commercial integration, the gateway's own developers provide personalized documentation and even direct guidance to help you get it working. The instructor also touches on what you'd need to do if your application supports multiple payment gateways. In that case, before the user reaches checkout, you'd add a payment method selection step. The user picks from options like Culti, eSewa, or cash on delivery. Based on their selection, your backend routes them to the appropriate payment gateway logic. In the current demo, only Culti is implemented, so this selector wasn't added. But in a real production application with multiple payment options, this is an important UI and backend consideration. The checkout form would capture the payment method, and the controller would branch accordingly to hit the right gateway's API. To bring this section together, today covered a lot of practical ground. The retry payment logic was explained and implemented, showing how to reuse the Culti API call with data pulled from the database for a pending order. The route was set up using a simple anchor tag, no form required. Orders were sorted so the newest appears first. A naming error with the order items relationship was identified and fixed. The review feature flow was outlined, reviews only after delivery. And the universal pattern for payment gateway integration was explained, which applies to virtually every gateway out there. Coming up next, the review feature and the final integration steps will be completed. Now, one important thing to understand here is that when you're sending money to a specific store, you cannot just use your own merchant account. Each store has its own merchant account. So if you need to send a payment to a particular store, you have to use that store's merchant account details, not your own. This is a fundamental concept. The payment must be directed to the correct account. Here's a key detail. The store ID and the dollar ID are actually the same thing. The store ID is the unique identifier assigned to each merchant or store. When you want to send a payment to a particular store, you need to pass the secret key that belongs to that store's ID. If you pass the correct secret key for the correct store ID, the money will go to that store's account. Get this wrong, and the payment won't reach the right destination. So let's walk through how payment routing actually works. First, you identify the store ID, also called the dollar ID, of the store you want to pay. Second, you get the secret key that is linked to that specific store ID. Third, you pass that secret key when setting up the payment method. And fourth, the system routes the payment directly to that store's merchant account. The secret key is essentially the authentication token that tells the system, yes, send this money here. If you use someone else's secret key, the money goes to them, so accuracy is critical. When you look at the transaction history or statements in your merchant account, you can actually see the balance change in real time. Before making payments, the balance was lower. After adding funds and processing payments, the balance increased. This is live. It updates as transactions happen. You can also see individual transaction records, including the product ID, the price, and the date. In the example shown, all the recent transactions have the same price, which makes sense because they were all processed around the same time with the same product. Here's an interesting distinction. From the sender's perspective, that is your account, the balance is not actually deducted. You can see the transaction in your history with all the details like product ID, price, and date, but your own balance stays the same. The difference is that the recipient's merchant account receives the funds, so the transaction is recorded on both sides, but the money movement only affects the recipient's balance. This is important to understand when you're testing or verifying payments. Don't be confused if your own balance doesn't change. Looking at the transaction details, you'll see fields like the product ID, in this case starting with 6T, the price, and the date. What's notable here is that when multiple transactions are made around the same time, all these fields are exactly the same. The user ID, the price, the product, everything matches. This consistency is expected and confirms that the system is working correctly. It's a good way to verify that your payment setup is functioning as intended. Let's wrap everything up. The core idea here is that merchant accounts are store-specific. You must use the correct store ID and its associated secret key to route payments to the right place. Transaction history is live, so you can monitor everything in real time. And remember, as the sender, your balance doesn't necessarily decrease. It's the recipient who sees the credit. All the transaction details, like product ID, price, and date, will be consistent for transactions made at the same time, which is a great way to verify things are working. Additional video resources and support will be made available to help you navigate this process. Topics like this aren't covered widely, so make sure to use the support that's offered.